Okay, so hi everybody. I'm not Love, the PI on the Victor project. I apologize for my very crackly voice today. I'll be very brief and let my wonderful team members continue with most of the presentations today. Just wanted to give you a little bit of background about Project Victor before we dive into specifically what we can do for U.S. educators. So what is Victor? It stands for Volcanology Infrastructure for Computational Tools and Resources. And it's a cloud-based platform for volcanologists where they can find, use, and integrate numerical models and other computational tools. It's been funded by NSF and NASA. The motivation for it really stemmed from community needs as reported, for example, in the 2018 Erupt report, when there were statements that highlighted the need for access to state-of-the-art models, having a communal cyber infrastructure to support a community, supporting community facilities that would promote accessibility and user-friendliness of computational approaches, and increasing their efficiency. So Victor is really trying to address all of it for the new platform that we built. It's coming on the tail end of past efforts such as VHub that was based on an older technology called Hub Zero that accumulated a whole slew of models where users were able to run either online or just download to their computers. Rehab was very popular in the early 10s, and then usage really went down, especially as its usage in classrooms, as well as the number of training and training events and workshops declined. So that's why we're really putting a lot of emphasis on training USR users and US instructors for students who are future users to really have a lively community. The goals of Victor are to make it easier to run computational models and tools, broaden model literacy. So even if people are not modelers, they still understand more deeply what is involved in modeling and computation. And at the end of the line, really reduce volcanic hazards by making models and tools more accessible. The Victor team includes myself and Sam Krasnov and Amelia Mullins, who are with me here at Lamont as the software engineer and training and education coordinator. Our collaborators are Sylvain Charbonnet and Charles Connor at University of South Florida and Abane Petra at Tufts. The planning for Victor included community discussions and virtual workshops where the design requirements were really formulated, then proposals submitted, and the pilot funded. Sam was hired 3 years ago almost, and then we had a workshop where first users were subjected to the very early stages of the platform. We have an advisory board comprised of people from different parts of both academia and government agencies, both in the US and abroad, that really tell us what community I think or need and put priority on. Overall structure of Victor, these are the headings from our website, which is really the main entry point, victorproject.org. The central piece is a hub portal that's based on Jupyter Hub technology that includes a model library engulfed in workflows in form of Jupyter notebooks, and then a whole collection of tools such as compilers, visualization tools, and then access to external databases such as NASA, NOAA, Copernicus, etc. On the website, you'll also see information about workshops and events, partners, our educational content, which Amalia will expand upon, and then an option to sign up as users. We have authentication options on GitHub, Microsoft, and Google, as well as link to our Read the Docs documentation and our communication channels with Slack, Discourse. This, you might be familiar with parallel efforts that have the same philosophy and structure, such as CSDMS, land surface dynamics, scoped for seismology, OpenSALab for in-situ processing, Anki for petrology, and Bengio for oceanography. Um, I'll skip some of the user experience slides because you'll see it in our demonstration in a minute. But I just want to say that we have both a terminal-based and a Jupyter notebook-based and a visual desktop interface, or kind of whatever fits anybody. I have a whole growing library of tools. These are just the modeling tools that we have for anything from lava flows and PDCs to magmatic and degassing processes. And new tools are being added continuously. And the fact that we have all these tools in the same place allows us to build kind of higher level workflows, such as model intercomparison. These are 4 lava flow models that all get the same parameters and input, and then it's very easy to just go step by step and compare them. We have new capabilities to interface with remote sensing tools, such as the higher level products from the Opera project that includes things like surface disturbance, vertical land motion, and water extent. For example, a Jupyter notebook where users can select an area, see what's available, visualize it, and then do some analysis such as segmentation. All right, we're walking towards higher level workflows like inversion and model benchmarking, and it is getting developed very quickly and is becoming available on the platform. This is the inversion workflow. An example where, for example, GPS data can be inverted using the D models and produce best fit and uncertainty on MOGI source. We're working towards allowing all these models that are currently available already on the platform to be coupled and in the future provide a way to look at uncertainties and relationships between magma chamber models all the way up to the gas and ash models. All right, Amelia is going to tell you a lot more about our education piece with examples. We've had a class that's been running for the last 3 years, computational volcanology, that is all available on the website. We're running workshops and events. So if this is your first time hearing about Victor, and it might be a little much at first, all of it is going recorded and shared on our platform, so you can always go back to it. Yeah, coming up is a field workshop. I don't have the image for it for some reason, but we have a summer workshop. We're gonna integrate field excursions with modeling of the processes that we will see in the field. So that's happening this summer. This is it from my introduction. I'll take it to Amelia to talk about more of the educational stuff.
Hi everyone, I'm Amelia. I am the training and education coordinator for Victor. I'm going to share my screen because I have a few slides to go over. Is it okay? Presentation?
Yep,
Yeah, great, thank you. So I'm going to go over the educative tools that exist and how to navigate the Victor website to find them, and then 2 examples of how they are being used or could be used. So for education materials specifically, there are 3 main sections on the website that are most relevant. All of these sections can be found by hovering over the education menu item in the main menu of the Victor website, and these 3 appear as tabs underneath in case I forget to say that for every section. But these tabs or pages include the For Educators page, which include the classroom ready materials or classroom specific materials, the training and tutorials page, which covers more specific topic in a couple different formats. And then finally, the third is what we're calling the educator interest form, which is where educators can reach out to us directly to give some background on their courses or their learners and express some more specific needs, maybe of materials that haven't been developed yet, and then we'll collaborate virtually from there. But more specifically, the For Educators page, like I said, can be found by hovering over the education menu item. And so this includes pre-developed course materials that are organized by topic, and they all integrate Victor into teaching volcanology in the classroom, generally at undergraduate and graduate levels. At the top of this page, there's a section that you'll see that's called featured content. This content is sometimes updated, but mostly it's just featured because it's either been tried in a few classrooms already, or it's more of a built out unit that also includes facilitator guides and answer keys. So they match together well and are included together here. Next, at the bottom of this page is the second section. It's this expandable menu that goes through the learning content by topic. So while this is always growing as we develop more tools, I believe that now at least almost every topic has at least one resource, as we included the lecture recordings from the computational volcanology course that Anat mentioned within these topic menus. So within these content lists are these take-home assignments. We are going to demo these.
Oh, microphone.
Sure. Switch. Okay. Are we switched? Okay, perfect. Great. Okay, hopefully that sounds a little bit better. So within this page, one of the content pieces are these take-home, what we're calling take-home assignments, but are designed as labs. The sections of these labs are sometimes and usually are divided into in-class and take-home, but those sections can be mixed and matched or changed according to the specific class's needs. And they all kind of follow the same format where it begins with procedures specific to Victor, getting started, registering, running the specific model, and analysis questions with the case study example and application questions. So this is the next section that I mentioned, the training and tutorials tab. So this, as I said, is more specific topic specific tutorials. And it has a couple different sections, which I'll go over and show you visual examples of. It starts with some background slides, which are just simple informational slides that can be included into pre-existing content where it's relevant. But I also wanted to highlight in this background section an introduction to Victor tutorial that covers the content briefly that is mentioned in the background slides, and a brief walkthrough, which is great for, I think, introducing new unit users to the platform without, a lot of overwhelm. The second part of this section is an expandable accordion menu that goes through specific procedures such as registering for Victor, and also a section that we are calling useful functions to know, which kind of is purposed to be like a quick reference guide if there are questions that come up, and has kind of developed into a sort of FAQ where if a user or a professor on behalf of their students has a question, the solution to that question usually gets added here. The final section, the third section of this page, is the tool-specific library. And so this includes these tutorials that I was mentioning in a couple different formats, which include video tutorials, procedural guides in the format of slideshow activities. I have an example here. So these are in slideshow format and go through the procedural steps without the entire context of a lab for running the models. So the reason I wanted to put these
two together is to show that while there is one section that is directed towards an educator audience with the classroom ready materials, both of these sections can be used to supplement each other. So this example is the preparation materials section for a lab that includes the same procedures for registering from the getting started with Victor section and links to one of the YouTube tutorials. So these are included in every lab already, but an example of one way to combine that has not been done before, but I think reasonably could be done, is including a the hands-on procedural guides that I just showed in this slide in a lecture deck just to introduce students before their lab if the time allows. So again, relevant to specific needs of the course. And then the final tab I wanted to show you is what we're calling the educator interest form. And this is just some background questions specific to your course, the level of the learners and materials they have. So we can see if there's materials that are already developed that might work for you, or if we need to develop more, which we're doing all the time, and very excited to get new topics that are needed from the community. So even if today we don't get to, maybe specific needs, or you just want to keep chatting, it'd be great to fill out this form and then we can collaborate virtually going forward and see what else might be useful. Sam is going to demo two labs, I believe, but I just want to show you how to find them on the website so that you can follow along if you'd like. So again, the education tab on the menu, the For Educators page has the topic specific menu, like I mentioned. The first lab will be that under Ash and Tefra, the Hazard Modeling and Engineering lab. And then the second lab will be under the Lava Flows menu, what we're calling the Lava Flow Modeling Mini Lab right here. So unless anyone has any questions about finding those or any other questions, I think we can move on to Sam.
All right, great, thank you. So, as Amelia said, so first we're going to start off with the Tephra lab. So I will share my screen real quick. Yes, my mic is on. All right. So, let me very quickly just share my entire screen. I'll just show briefly. I'm already signed in, but what it'll look like when you first get to the hub. So just for reference, you'll see this nice little splash page and our logo. We work with 2I2C. They're the ones supporting this kind of infrastructure. Our team filled it in, but they're making sure the architecture is stable. And then you log in. We have a couple of options, as you can see here. It's GitHub, Google, or Microsoft, and that hopefully should fill, 98% of cases. So, yeah, if you have a Yahoo account, maybe it's time to upgrade. But once we're done with that, we can you'll log in, you pick a machine, and what you'll end up seeing is something like this. So I'm going to just real quick change to this. Okay. And so for the Tephra lab, what we'll start with is there's a command called Victor. So if I just do Victor, you'll see it's just this command line tool that does a couple of different things. In this case, we're going to use the setup command, but we have ones for benchmarking, for testing, for updating, and then we'll expand on it, as time goes on. All right. So we can I'll clear that, and then now we have a big list of models, and what we can do is go right to Tephra 2. It's at 17 there, so you just type in the number, and then we'll give it a second. if you look on the right, it just popped up a little folder for Tephra2 right there. And if I open it up, we have the executable, and then we have a notebook. And for now, those are really the only two things we need. And the notebook will actually create everything else. So this is one of many of our notebooks. For those who aren't familiar, Jupyter Notebooks, it's generally used with Python, but can be used with a bunch of different languages. It allows you to kind of make an interactive book or workflow. So at this top, we just have a bunch of markdown and text explaining what is Tephra2, what is this workflow supposed to do, and what are some of the steps. So, and then we have the references here. And then generally, we also try to make it very user-friendly. So even if your students are not necessarily, very computer literate, we make it very clear and explicit which areas should be run without any alteration, and which need to be edited for a specific project. So can start running through. This is, as Python is, just all the libraries we need to get everything working. So I can run that. It'll take a second. I'm just going to make sure that I have the right coordinates. Okay, yes, those are good. So then we can run this. This just stores the variables. And what we're going to do first actually is use something from the Victor library. It's functionally it's a bunch of helper functions. In this case, it's to download a DEM from the Open Topography database or project. And we've just made it into one line of code where you specify just the triangle around it. And then we can also specify if you want it in an ASCII shapefile or a GeoTIFF, where you want to get it from, and then the output name for the file. We also have there's other functions in the PyVictor library for visualization, and then we're starting to add some for Bayesian statistics, and at some point we're also hoping to have some of the inversion code included in that library as well. So if I run this, give it a second, it should get all the data we need. It'll say this little output at the end that just says file was downloaded as the name. This one is a bit of a larger file because we're trying to take about 2 degrees of latitude, but there we go. So now we can continue on. This cell is just getting us between UTM and lat long, but now we're actually going down to the important part. If you look at the notebook, you'll see that we're specifying different eruption masses. The students would have to calculate between the eruption mass and volume, but in this case, where the model takes in the eruption mass, so that's just kind of a little extra on top for the students. But one moment. Just want to make sure that everything stays on track. All right, so these values are actually good to start. This is about this first value is about 1 cubic kilometer of erupted volume, so we can run this. These are a bunch of other more granular values. So if you have students that are a lot more familiar with ash dispersal or these kind of dynamics, you can specify the grain size and the grain size distribution, the threshold for the fall time, the type of plume model you want to use. There's just a lot of granularity. We have it all set to defaults that are you know, very plausible, like very appropriate for the situation, but if we do have also this flexibility. So we can continue on. This is all good. The grid file is automatically set up, just a way to pick the spacing of where you want to actually test for the grid file, or test for the tetrafall. So we can continue running, keep going. In this case, there's a couple of approaches you can take. You can either do it in these set up an actual grid, and these we're actually specifying particular points. These are different towns and cities near South Sister. And we're picking these lat long, the elevation, which is 1,000 meters, and then just setting these all up and putting them into these input files. So if you look on the left in a second, that file should also pop up. Yeah, so now we have a grid file. We have our DEM, and then continuing on now, this is kind of another example of us and Victor trying to pull data from other places. This is, you know, I think it's about a day delayed, but it's hour by hour wind data that's worldwide. So you can specify the exact parameters for the historical eruption. So I'll run through these, keep going, and then here we pull from the API. So it takes a second. This might be in red, but it's nothing to worry about. It's just running through and making sure we can get the data. So the status has been updated to accepted. It's just going through a waiting process, but in a moment we'll have that. So yeah, it's running now. In the meantime, I will let these keep running. This is all kind of background code. It does not have to be like worried about by any of these students. It's just get all the data and then make sure it's formatted correctly for Tephra2 to run. So load the file in, make it structured correctly, and then put it into a WIN file. Finally is the actual config file. Most of this data has already been set up. We're setting the vent easting, northing, the elevation, the plume height, the eruption mass, all those things that we talked about earlier. Again, we provide this just in case people want to look into exactly what we're doing, what exactly the code or the model needs, but this can be run at this point. Every variable is set up properly. So finally, we've got all of our data ready. We have the configuration file, it says, we've got the grid file and the wind file. And now we can actually run Tephra2. So if I run this, give it a second, the model first just spits out all of the information we gave it just as kind of a sanity check. But if you give it a moment, it does end up outputting all the data we need. And you can see actually the node underscore file is the default output, and then we pipe it into a CSV file, which is much easier for everyone to use. So in a moment, those will finish getting filled up, and we can actually work at looking at the output. While this is running, I will take a quick aside and then go back to the actual excuse me, the actual workflow or the homework assignment. So in this case, you can see we have a lot of what I just told you guys, but this is nicely formatted for all your students right from the beginning. Start the launcher, here's your server options, pick a machine, pick Tephra 2, and now we can set it up. So set the mass eruption value, which I mentioned earlier, we're obtaining a wind file, and then we set up those points of interest. So at the top, we actually have students, we give 3 examples of towns, and ask them to apply, figure out the latitude and longitude, figure out the coordinates, and then also the roofs, because in this specific example, we work with a professor who had a class heavy in engineers, specifically civil engineers. So we wanted to not only just run the model and get people comfortable with that, but also say, okay, now that we've gotten this data, what do we do with it? We can actually see, uh, does this ash, does this tephra fall pose a risk to these towns? So if we go back, we can see it's completed. These files are now, this is all full of data. And we can continue on. This loads the file, formats it how we want it, and then what we have at the end of this workflow at least is a very nice little visualization. So what you can see here, this little triangle is the eruption point we specified for South Sister, and then right, at least in this example, we just have these little stars that show those points of interest, and then the thickness in centimeters of the ash deposit, at least in our points of interest. And then we have all the dispersion in isomass contours. So once the students will have this, they can go back now, put in all this data, and then say, okay, what is the total mass on the roof? We will ask them to do it a few times in different sites with different eruption volumes. So they'll go back to the top, change the volume, continue on, and by the end of that, they'll have that nice little table of data. And then we have some kind of review questions, make sure that the students did their work. Which direction did the output travel from? And in this case, we're asking for a cardinal direction. And then on the next page, you can see right here, there's actually something talking about the threshold for different types of roofs, and then the average collapse load. So we can refer that against the data we got, use the density that of the tephra and then the thickness of it, and then use that to actually determine is the roof stable, will it collapse? That is the overall idea for this first workflow. This was one of the earlier ones we kind of did that we did with a professor, and we worked to kind of personalize as much as possible. And this is what we hope to do for any of you that are interested. Continuing on though, I will also show one other that's using another kind of visualization library from Victor and one of the lava flows. So we're gonna just do a quick version of this. It's just running molasses, which is actually created by one of our co-Is, Chuck Connor. So similarly, in this homework, we give a few objectives. We're getting familiar with Victor. We're getting this real world data, excuse me, and then in this example, I'll just show you molasses, but because we have at this point 6 or 7 different lava models, it's now possible to compare and contrast. As Anat said at the beginning, we have some benchmarking implementations, even though that is a bit higher level. though, yeah, so in this example, we're taking a 2022 Mauna Loa eruption and doing some comparison. So some data to get the users prepped. And then first we take a look, let's see, this is the actual footprint. How far did it end up stopping from Saddle Road on the Big Island? So kind of get the students engaged, see what the, what are the stakes and what are like, let's contextualize everything. Similarly here, instead of, we're gonna do the same thing back here, but instead of going for Tephra 2, we'll go for, so we'll go for molasses, which here is 12. Give it a second. This will always pop up just to the left. This is your home directory. Every user, every student will have this. Theirs will be less crowded than mine. It starts off with just a desktop folder and then the shared folder, which is where we have our all our models, our teaching materials, and this is open for everyone. Okay, there, molasses appeared just now. We have this is also the default DEM associated with molasses. So we have Mauna Loa DEM, we have the executable, and this one, again, very similar to before, but because it's a statistical model, it actually runs much quicker and has much fewer parameters. So we can run through, get the packages we need, import the Victor library, and then let's see. In this case, we just provide the total volume, the volume per pulse, and then the residual thickness. For those who are interested, this model uses the cellular automata approach, but really all we need is name of the DEM, total volume, pulse volume, residual thickness, and then they call it events, but in this case it's the UTM location. It's just the coordinates. So we can run this. This sets up that the file with all the values we just got together. And then we have a little plot DEM function if we give it a moment. You have this nice little view of Mauna Loa and right along the ridge. This is, at least in the 2022 eruption, where the later lava flows went. So we're trying to see basically how far up along this path it goes. So now that we're done with that, we can run the model. This is basically just make sure we have the right DEM, make sure we know where we want the eruption to be placed, and now we can just start running. So if we give it a moment, you can see it goes very quickly, and it's already done. So it outputs into this kind of arbitrary file, but what we do for the users is get the data, format it correctly, and then save it into a proper ASCII shape file for them to use in something like QGIS. So that's what we're doing right here. And if we give it a moment, you can see this is a bit zoomed in, but you can still see the ridge right behind that. We also just got the molasses.asc file, and so that's useful wherever. And we have a nice little lava flow here. Again, I'll refer back to the actual homework, the actual classwork. I just verbally said it, but if you are following along, that's almost exactly what we were doing just now. So we're making sure the DEM works, but we can make functionally just one or two changes, and in the end, this has a slightly different initial condition, but you can see generally we get a nice visual output that you can also save. If you just do Shift, you can just save image as, and save that to your desktop. Also, just to clarify, this is all in the cloud, so there's no need for all you need is an okay connection. It doesn't have to be fast, just some internet connection, and you can access this for free. Let me make sure I didn't miss anything. If we had more time, we would go on, run it multiple times, different volumes, measure the length. You can see here we actually have the easting and northing, so we can see, oh, this is about I think this is about like it's either 500 or 5,000 meters. I might be off by an order of magnitude. But now we can start doing measurements if we zoom out. So if I did zoom equals false, we can actually see. If I give it a moment. So now you can see it's a much smaller flow but if we did it with a larger volume, we could see how much farther it got, and that is a nice little activity for the students. And then to visualize it in yet another way, we ask them to graph it as well. Some follow-up questions: what volume is required based on the inputs we gave, and then in the kind of full version of this assignment, they take another model called Mr. Lavaloba, which works slightly differently. Use that and then compare the two of them and contrast. So then you can actually go to the map at the beginning, which I'll go back to briefly, and then kind of reflect and see, how do these models kind of line up in some areas, and how are they very different, and what does that say about them? And then we also try to get everyone to communicate and like post their findings. So in this example, we do Padlet, but it can be your Canvas, your Canvas forum or for the class or some other version like that. And I think overall that's it for the demos. If there's any questions about the uh class materials, the homeworks, the platform itself, and anything else that I might have missed, feel free to ask now.
Also, one of the things that we wanted to hear from you all is what you guys are looking to do, is we're really here to serve. And we have a quick poll that will pop up on the side, just a couple of questions. And if you guys have thoughts about things that you're teaching or you would like to see, I also want to say we only showed 2 examples here, but there's a lot of materials that are already available, like they're shown, and we're working on labs that are for petrology with Penny Weezer, and a whole other slew of things, basically what people are requesting. So in addition to this quick poll, just so that we have an idea of who was in the webinar, there's educator interest form on our website where we ask for a little bit more detail so that we can really make something that's tailored for you. And so if you have a question, you can raise your hand or unmute yourself and just ask. It's a small group to do that.
Yeah, you can unmute.
Allison can.
Sorry, Allison, can you say that again? Yeah, all right, we might not be able to hear you. If you want to type it out, we can also answer that way.
Oh, yeah.
The interest form on the website, right?
Mhm.
There now, yeah, it's, yeah, for indication of what you might need in the future for, I mean, future or current, we've had, you know, both, filled out, so. If you have something coming up, that would be perfect.
Yeah, and we can also though our team is small, so maybe implementing an entire course of materials might be beyond our scope, but we can definitely talk with you, plan, and especially if you want to use Victor for many of your assignments or your lab work, we'd be happy to help you get that set up and make sure all your students and all kind of the infrastructure is set up so the assignments can go off without a hitch. If people do have further questions that come up after the lab, or sorry, after the webinar, you can email, it's,
It's Victor
yeah,
and the
then Victor at LDO.Columbia. Right, that will go to all of us and we'll be able to answer any questions you have. Again, they can be about the webinar itself, about the educational tools, about the computational tools, about anything in between. Yeah, so please don't hesitate to reach out if you have questions that you want to ask in private or that are just kind of more detailed than something quick right now.
Well, thank you all for coming today.
Yeah, I can put up a website. Built by some. Oh, I've been accidentally messaging those to you. Okay, sorry. So it's our email is victor.ldo. And then our website is the Victor. So, okay. Yeah, so there you go. That should give everyone the context you need to get in touch with us and learn more about our platform. But I hope that you got a nice overview of what we have to offer today.